Okay, so thanks, Keith. So as was mentioned, I'm going to talk about plasma formation in this thing called a post-hole convolute, which is a device used on Z. So when I started this work, I was at University of Michigan, and Ron is my advisor there, and then a number of other people. Mike is my manager now, and a bunch of other PIs at Z that let me do ride-along shots, and just people there that in general have helped me out with this experiment. And then some support that we got from guys at Weizmann Institute doing basically some of the spectroscopic work, and then some simulation support that we've gotten from these guys at Voss Scientific. So in my talk, since I'm not really sure exactly what everybody's background is, I'm going to talk about what Z-pinches are very, very briefly, what the Z-machine is, and then I'm going to discuss what post-convolutes are. I'm guessing that people have heard of Z-pinches and the Z-machine, the convolutes maybe not so much. Then I'm going to talk about the diagnostic that I was using and just give a quick sample of what the spectrum that you might collect with it would look like. And then I'm going to talk about the actual measurements, which more or less I'm studying where a plasma forms and how quickly it moves within a particular device. And then I'm going to talk about what this means. So I guess the first thing to mention is why do we want a Z-pinch, or what's the purpose of these? So you can use a wire array or a gas puff Z-pinch, which I'll show on the next slide what these things look like, to create an intense X-ray source. So people have used them in the past to create up to 2 megajoules of X-rays as a roughly 200 EV Planckian blackbody, or also as a K-shell radiation source with a lower energy, or lower yields, but higher energy in the KeV range. So you use this potentially to drive some sort of ICF fuel capsule, and the higher energy radiation you would use for some radiation effects experiments. And then there's also certain applications you can do laboratory astrophysics on a machine like this. A relatively new idea that has only really come into play largely on the machine in the last couple of years is this cylindrical liner that you can drive magnetically, and you would basically have a solid liner with a gas inside of it that's heated using, say, like the beamlet laser pulse. And then you can compress that down and create an inertial fusion reaction. So that's potentially one mechanism for this IFE programs that people have been pushing. You can also use this to achieve dynamic material pressures that are much higher than you could with like a radial flyer plate. And this is basically because you're compressing in sort of 2D instead of 1D. And they've also used this to look at the growth rate of the magneto-Rayleigh-Taylor instability on Z. So what does a Z-pinch look like? So you have an array of, cylindrical array of very, very fine wires. So these are on the order of a tenth of a human hair in diameter, sort of 10 micron range, but it's tough to really understand what that is. Basically, you apply a current through the wires, and that creates a magnetic field that runs around azimuthally, and you have this J cross B force which compresses these wires. Basically, they're being heated and converted into a plasma and then collapsed on axis to create this pinch column. And that column actually is what radiates the X-rays at the stagnation point. So one thing to note is that roughly the power scales as the current passing through the wire is squared. So a small increase in current actually has a significant increase in the power. Conversely, say a 20% current loss, which will be important to mention later, has a significant effect on the power that's radiated. So that's Z pinches. This is the Z machine, which is used to drive these pinches. Keith might recognize this. I stole it from one of his papers, but I referenced him here. So the Z machine is roughly 30 meters in diameter. I think it's 35 or 33, something like that. On the outer edge, you have a Marx bank here, which is basically a series of capacitors that they're charged in parallel, and then there are a bunch of switches closed connecting them that cause them to discharge in series. So on Z, they charge to about 80 kilovolts, and then when they discharge, this is up to, well, I think it's 60 capacitors. So at this point, it's roughly 5 megavolts coming out, which is discharged into these basically intermediate storage capacitor here, which is used to compress the pulse. You have laser triggered gas switches here. So that's used for timing. Z actually has the capability to do pulse shapes, so you can drive specific isentropic compression experiments with that, and or you can change the machine so you can either fire it in 100 nanosecond rise time mode or in 300 nanosecond rise time. So you can use those to set your timing, additional transmission lines, and basically just bringing the pulse in further to this point here. So you have 36 of these modules initially, and you're bringing it into the insulator stack where all that current is combined together and then split up again into 4 individual magnetically insulated transmission lines, or mitals. So at this point, you're transitioning from a water section to a vacuum section, and then you're bringing the pulse in further. I should note this is about 10 feet in diameter at this point. So you're bringing this pulse in further to a load here, which is roughly, say, 1 centimeter tall and 1 centimeter in diameter. So you're bringing your pulse in by essentially 6 orders of magnitude compression in shape. You're charging this on sort of 100-second time scale, and you're discharging on 100 nanosecond time scale. So 9 orders of magnitude in time. So you got about 15 orders of magnitude in pulse compression, or in energy compression from here to here. Now, what that does is you have a very high power flow through this region, and that actually causes some issues. So these transmission lines shown here again, so you have in blue the anode and in red the cathode. So you actually have 4 AK gaps, 1 here, 2, 3, 4, and then you're bringing it together into this load up here. So you measure the current out at this region, where the current density and hence the energy density that's flowing through the transmission line is still relatively low. And that gives you this current shown here in black, the mitral current, which again, magnetically insulated transmission line. You have another B dot shown here, which is just inside of this convolute that I'm going to show you a little bit more about in a minute. And based on these B dots here, you get a load current that is significantly different than the mitral current on certain shots. So what does that mean? You have this drop in current, which is on the order of 20%, which, as I mentioned before, for a wire array, current or power scales as approximately current squared. So that's 30, 40% reduction in your power that's radiated, which is significant. And as I mentioned, you have this compression of energy flowing through the machine that at this point you have such high energy densities that you start to get plasma formation, which basically kicks off hydrocarbons that are absorbed into the material. And that causes a gap closure, which can short out your pulse and drop the current by significant amounts. So the actual post-hole convolute itself is sort of really simple idea, but really complicated at the same time. Basically, all you have is you have 2 transmission lines that you want to take the current from both of these lines and connect it into a single transmission line here. So you have your anode that you're running current along on both cases, your cathode that's shared between them. You punch a hole in the cathode and you use a post to connect the anodes, hence post-hole convolute. The complicated thing is if you use your right-hand rule, you have current flowing in this direction in both cases, but the magnetic field is actually into the page here and out of the page here. So if you follow that, at some point, there's a transition between into and out of the page where the magnetic field goes to 0. Now, when you're relying on your magnetic field to insulate your transmission line and it goes to 0, there's some problems. And these magnetic nulls, which is what these areas are called, they do potentially cause some issues in these regions. And that was originally thought to be the reason why they were seeing all these losses. Some of the losses are a result of that, and some of them are a result of gap closure that's actually located roughly here. So the Z post-hole convolute is a little bit more complicated than the picture I just showed. So they have 4 transmission lines, not 2. So you actually have to stack 2 of these on top of each other to get the combination of the 4 gaps into a single gap with your wire right here. And then additionally, they actually have a 12-fold azimuthal symmetry, which is basically to try and make a uniform current around this, and it also acts to reduce the inductance in this region, which is important for having a fast rise time and a high current pulse. So as I mentioned, the guys at Voss Scientific, particularly Dave Rose, did a bunch of simulations of the convolute on Z. So shown here is basically the lower post, the upper post. This is where the load is, and you have your 1, 2, 1, 2, 3, and then kind of off the screen 4 transmission lines coming in. The plasma is shown here in sort of this rainbow of colors, and you can see that they're primarily modeling just the cathode plasma that's forming within the post holes themselves. And so what they learned with these simulations, which were originally done as particle and cell, just electromagnetic simulations that allow electrons to flow, is that if you don't include this plasma, you don't get the losses that they observe on Z. You get maybe 100 kiloamp loss, which still 100,000 amps, that's kind of a lot, but it's not the 3 or 4 mega amp loss that they actually see, on this shot on Z. Now, when they include these plasmas, they get the red dashed line here, which roughly follows the midal current and the load current for this particular shot. So they feel like they've done a decent job of figuring out, yes, you need to include this plasma model in here. Now, the way that they actually include the model is that they assume some desorption rate of a certain number of monolayers per nanosecond. That's fixed. Once it turns on, it keeps going. It's always the same at every part in the convolute that is turned on, regardless of how much energy is deposited there. So it's a pretty crude model, and what we're hoping to do is try and identify some information about this plasma, and then try and use that to backtrack what sort of desorption rates and try and basically help out the modeling community for this. The reason why you want to do that is because the losses that they saw in these post-hole convolutes started out at, on PBFA2, they were low enough that they didn't really measure anything. As they increase the power going into the Z machine, when it was renamed from PBFA-Z to Z, they saw maybe 5, maybe up to 10%. Now when they upgraded to ZR, the losses in some shots has gotten as high as 20%. So as they're flowing more power through this region, they're seeing this greater loss, and that's sort of the motivation that if we're going to go to a larger machine, how is the convolutes going to scale as far as its efficiency? So the measurements that I'm making, basically, this is where that B dot is located, the load B dot, and I'm replacing that, as shown here, with a probe that observes the visible emission from the plasma that's in this region. So here you have your post, here's the cathode, and the hole is here. Basically, I have, it's a streaked visible spectroscopy system, so it has spectral and temporal resolution. It's fiber optically coupled, so there's more or less no spatial resolution other than what region of the convolute the fiber is able to view based on the limiting aperture that I apply to the end of it. So this is a sample of some data that was collected. Shown in blue is the actual data, and then shown in red is this fit that's used. Basically, the absorption feature shown here, well, this is continuum emission with an absorption feature and timing fiducial, so we can ignore this. The absorption feature is hydrogen H alpha, and so you can look at the spectral broadening of that and try and determine what the the density is of the plasma that you're observing. So on a particular series of shots, we actually were trying to identify whether the plasma we were seeing was the plasma that's observing or forming down here, or there was some theory that electron bombardment of this region, which is actually the B dot cup itself, could be producing a plasma that we could be observing. And so to try and identify whether or not we were seeing, we thought we were seeing, we put this lithium fluoride dopant on the post itself. And so that should expand out into the gap, and then we should see these lithium fluoride either emission or absorption features. And that would be an indication that we were actually looking down into the convolute because the lithium's not located up here. And so what we actually saw, which for this one position here that I'm showing, we saw this absorption feature at 6708 angstroms, which is this lithium 2s2p transition. It's neutral lithium. It's was used actually to diagnose a lot of the PBFA2 ion diode experiments. So it's a well-known transition. So we see that being backlit, which means that the continuum plasma that we're normally observing is actually below wherever this is expanding out into the gap, or at least some fraction of it is. So we have an idea that, okay, the plasma we're looking at is in the convolute and it's sort of below this region. And then for the lower position where we put the dopant down here, we actually see no absorption feature, which is an indication that the continuum emitter is actually sitting more or less above this plasma that's expanding out into the gap. So that gives us sort of roughly here is where we think that the plasma is forming. So if I take where I put those dopants and I compare it to where the simulation says the plasma should be, well, this is sort of the chunk of plasma that we think we're looking at, and yeah, that happens to fall in between where these two dopant locations are. So we've talked about some additional experiments where, say, we might slowly step our way back up to here and see how much the absorption feature shows up and how it changes in shape as a function of the position. And that would give us a better idea of where this plasma is. But of course, these shots are pretty expensive, and I don't get all the time that I'd like on the machine. So some other experiments that happen to be run in the meantime. So this was looking in the exact same region of the convolute for two different shots. The difference between these shots, basically, this one was a wire array shot. So those really high losses that we saw are always on these wire array shots. You see a slightly lower loss shown here in green, which is maybe like 10% or less. This is for one of those cylindrical liners that I mentioned at the beginning that they're hoping will prove useful for inertial confinement fusion eventually. So looking at those two particular shots, we can measure the plasma density as a function of time by looking at basically the change in the profile of the line shape. You can see that for early times, this low or the high initial inductance, low time-changing inductance shot actually has a higher density. And then at some transition point here, the higher or the lower initial inductance but high L dot shot, which is the wire array high loss shot, takes over and the plasma density goes up. And this sort of makes sense based on the power that you have flowing through the convolute. It's sort of a marginal difference, but there actually is a difference where the initial inductance creates a higher voltage in the convolute. So despite the fact that the currents are roughly the same up until this point, the voltage is higher. When you start to get the pinch imploding on axis, you have this L dot, which drives a voltage spike, and that's what causes this late time jump in the power from the wire array shot. And so if you kind of look at the timing between when these things, the initial start of the current and when this happens, and the start of the loss current and the start of, or the crossover point here, you can get a rough indication of what this closure velocity might be, which is 10 to 20 centimeters per microsecond, which is actually quite fast for these sorts of plasmas where the densities are as high as they are. You know, I guess that's something to note, is that the peak densities we're looking at here are on the order of 10 to the 18 per cubic centimeter, which is actually quite high. So another measurement to sort of confirm this plasma velocity that we think that we're measuring, we look down into the gap at 3 different angles for nominally identical shots, and then just look at the turn-on time we get of this continuum emitter. So here these 3 angles are overlaid, and you can see there's some overlap in them, which is sort of indicated here. You can see that the turn-on time for the 3 different shots are very close to each other in time, but there's actually a distinct progression from cathode to the gap to the anode measurement. So you basically are monitoring a plasma coming off of this surface and traveling towards the post. And based on these measurements, you can get estimates up to 40 centimeters per microsecond, but realistically on the order of 20 centimeters per microsecond. And so the last set of measurements I just want to briefly discuss is sort of another attempt to confirm this measurement, looking at 2 different regions, and rather than looking at when the continuum turns on, looking at the basically the change in the line density, or the line profile of this hydrogen absorption feature as a function of time at 2 different locations for shots that have essentially the same current, which you can see the loss current that's observed here has roughly the same. This is the difference between the anode, or the emitter, and the load current, basically. So you can see it comes up to about 3 megaamps and then holds relatively constant there, and it has similar turn-on time. So the density for the cathode case basically always sits above the density measured for the gap case. And so at any given time, you can say, okay, the density here was a little bit higher, but what actually is kind of interesting is if you look at what at a given density and you pick off when the cathode case observed that density, and you find that time, and then you do the same thing with the gap, you can get another estimate of what the closure velocity is, which again we get on the order of 20 centimeters per microsecond, which for those of you who don't know anything about mitals, which I don't know if a lot of people would, usually you would expect this to be on the order of maybe 2 centimeters per microsecond, but the intense electric and magnetic fields that you're seeing in this region have this ability to sort of change what this closure velocity would be considerably compared to some of these other experiments. So just in summary, using these lithium dopant shots, we were able to determine that we were observing a plasma in the convolute, and we set some loose axial bounds. We'd like to do some additional experiments to get a better fix on where that plasma is located. We have inferred the densities up to 10 to the 18 per cubic centimeter. So we have this sort of plot of density as a function of time for a given view. It'd be nice to have a little bit better idea of where we're looking axially, and then maybe we can backtrack this and compare it with the simulation to try and give them some more bounds on how their models should bring the plasma into the convolute. We have shown that the plasma density is dependent on the load impedance history, which, since the loss is also dependent on the load impedance history in a very similar manner, this is a good indication that the plasma that's forming is actually causing these losses. And we also have established that the most observable plasma is actually crossing the gap from the cathode to the anode, which originally there was some question as to whether it was moving anode to cathode or vice versa. And that the apparent closure velocity is on the order of tens of centimeters per microsecond, which is about an order of magnitude greater than we were expecting. So why is this all important? As I said earlier, postal convolutes, you basically need them to create these fast rise time, high current pulse power drivers. And so if we're going to create future ones, we do have to have some idea of how we should design these. We've seen that the losses have increased significantly as the power that's going through them has increased through different machine iterations. So it's actually very important, for future designs where we're going to have higher power, that we would have additionally some sort of way to mitigate these losses that likely will also increase. It seems that the plasma dynamics are actually quite important to understanding the losses based on these experiments and the simulations that have been run. And we sort of need these experimental data to determine how to model the plasma properly in the simulations. And this is sort of the beginning of these experiments. As I said, I started out at U of M working on these. Now I'm at Sandia, and I'm sort of continuing this study. So hopefully I'll have something interesting to report on this again in about a year. And that's all I have. So thanks.